Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a theoretical physicist, which means I'm a cosmologist, which means I'm a theoretical physicist. I'm both. Sometimes, I have this well-rehearsed intro, and sometimes I do it on autopilot, and then I make mistakes. So I should always pay attention to what I'm saying. So, yes, I'm a cosmologist. So that means that I study the universe, the contents of the universe, how things evolve, how things interact, basically all of the stuff happening inside the universe. It's great fun. I love being a physicist. I love being a cosmologist. And I love chatting to everybody about all of the cool things I get to work on. So for anybody who doesn't yet know, the idea, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about physics, about space, about academia, about cosmology, about myself, about Finland. It's an ask me anything. You can literally ask me anything you want. I won't necessarily have all of the answers, but I will do my best to answer all of the questions you might ask me. If you're a first-time viewer, welcome. If you're a regular, welcome back. If you haven't done so already, please do subscribe, like the video, leave a comment, say hi in the chat. It really, really does help boost engagement, and I really do appreciate everybody who presses buttons on YouTube or on Twitch and makes stuff happen. I see we have a couple of the regulars in already. We have Paul Mito, Jean, Press, David Howland, Sophia, and it's great to see everybody here. Great to see all of the regulars, people from very different countries, very different backgrounds. Great to have everybody here. And let's see, we already have some comments. I see there's a comment from Paul already. My daughter Robin says hi. She's visiting and here to steal me away, so I'll miss today's chat. Thank you for the really nice comment, Paul. I remember chatting with Robin. She's a lovely person. Say hi from me, and of course, go spend time with your family. Don't worry, you can always catch the replay. No, this is a live show, but there's always a replay. So thank you for stopping by and saying hi, and go have fun with your family, Paul. I see we have Mito saying hello as well. Bunch of the regulars coming in. Alok, Shwansi. Great to see everybody here. Scott as well. All of the regulars. See, comment from Mito, waiting for the Perseid maximum tomorrow, and there should be a clear sky in Helsinki. Yeah, so it is an exciting week in terms of astronomy. There is a meteor shower happening. This is one that happens every year. So there is basically a cloud of asteroids, and every year our planet travels through this cloud. This means that when this happens, there is a higher chance of seeing shooting stars, meteorites, things falling in the night sky. It always peaks around the weekend or around the 11th or 12th of August, and it's a yearly event. Some years we get more, some years we get fewer, but it is one of the most dependable things. If you want to see shooting stars, this is one of the biggest ones of the year. This year is not as big as some other years, but this year there's not as many as other years, but there still should be a good amount. So if you have a good visibility, even in a city, there's a high chance of seeing these, even if you don't have a lot of darkness, which is great for seeing things in the night. There is a high chance of seeing them. So you want to head out after dark and look kind of northwest if you're in the northern hemisphere. I don't know exactly where. I know approximately in Europe it's northwest. I'm not sure in other countries, but you can adjust slightly. And if you're in the southern hemisphere, of course, that's going to change a bit. But if you're in the northern hemisphere, you want to go and look northwest. And the best time to do it is tonight after midnight. So if you're still up in a few hours in Europe, go outside, look for the meteor shower, look kind of northwest direction, and you might be able to see some shooting stars. So northwestish is kind of the radiant, and they should radiate away from there. So you can see them in any direction, but that's kind of where you should focus. And we do have a clear sky in Helsinki, despite the fact that it has been raining consistently for the last 2 or 3 days, on and off. There has been a lot of rain. There was some storms as well, which is lovely. But now there is a clear sky. Tomorrow is supposed to be clear sky, so we should be able to see some in Helsinki tonight, tomorrow night. If you have a good sky, go out and check, because you might get to see some cool shooting stars, which is always fun, and it's nice to just look at them. I believe it's in 2 or 3 years. It's supposed to be really, really intense. We're going to get a lot more shooting stars on average. But this year is kind of an average year, but there should still be some, and it's still very cool. Have a comment here from Sophia. I forgot to tell you this last Friday, but my AirPods broke the day after last week's stream. Haha. Yeah, devastated by the wireless headphones slander. See, this is what happens if you have wireless headphones. If you had ones with wires, that wouldn't happen. Well, it would, but not as frequently. But yes, I do enjoy the yes, I do enjoy headphones and earphones with cables. This is an ongoing thing. Okay, there's a comment from Shwani here. As always, I'm just picking your names from the YouTube messages here. If I mispronounce your name, or if you want me to call you something else, just put it in the comments here, and I will do my best to remember that. I try to remember all of the regulars. So if I, I'm just pulling names here and going with what sounds best to me. But really, if I'm mispronouncing your name, if there's another name you want to go by, just put it in the comments, and I'll make a mental note of it. And then I think it's important to call people by their actual names, or the names they want to be referred to. So just leave me a comment, let me know. So there's a question here by Shwani. How long does it take to become a cosmologist? This is a great question. So there's the question there of at what point can you consider yourself a cosmologist? Do you need to be doing research? Do you need to be getting paid for it? I think you become a cosmologist as soon as you're applying the scientific method to study the cosmos. That's it. That's my definition of being a cosmologist. Now, usually the path towards becoming a scientist is doing a lot of studying. In my case, this was a bachelor's degree in physics. This for me took 5 years because I was working during my bachelor's as well, and I slowed things down. So I took 5 years for my bachelor's. I did a bachelor's degree in physics. Then I did a 2 years master's degree in astroparticle physics and cosmology. And then I did a 3-year PhD program in cosmology, early universe cosmology. 3 years is a very short PhD time. The average in most countries is 4 to 5. In Europe, I know in the US it can be 6 or 7. So 3 years was kind of a short PhD, but it's the length in Germany. Personally, I think 4 years would have been better. I would have benefited from a 4th year on my PhD, but I think 3 was okay. So that means that if you count my studying time, it was 10 years where I could still refer to myself as a student. And then I started, so this was starting university for me at 18. So then I finished my PhD when I was 28, which is a few years ago by now. So yes, so for me, it was like the 10 years of studying, and now I am just completing the 5th year of postdoc and about to start my 6th year of being a postdoc. That does mean that I'm still in this kind of in-between stage where I don't have a permanent job. I'm not yet a professor, not yet an assistant professor or an associate professor, but also not a student. So kind of in this limbo in-between stage that we call postdoc, which can last a lot of years. So when did I become a cosmologist? I would personally think that I can count myself as being a cosmologist during the second part of my master's degree, when I was doing a master's thesis on cosmology, and I was part of a research group working on a research topic in cosmology. I was not being paid to do it, but I don't think you need to be paid to consider yourself to be in something. So for me personally, I would say I became a cosmologist during my master's thesis on early universe cosmology and inflation. So to answer your question, how long does it become a cosmologist? Well, I think if I'd done my programs as quickly as possible, it would have been 8 years. So that would have been 4 of the bachelor, 1 of the master's, 3 of the PhD. I slowed things down a bit. So for me, it was 10 years to finish the PhD, but I think already during the master's, you can consider yourself a cosmologist or a physicist. So 10 years, I would say, to finish the studies required, but I think it was probably a shorter period than that. And I do think that being a cosmologist, being a scientist is an ongoing process. It's not a finished thing. I think the learning is ongoing, the discovery is ongoing. And while I know more now than I did when I started my postdoc in Finland. So yeah, it's a continuous process. We continuously learn things and evolve and progress in our scientific journey. So I think that the journey to become a cosmologist never really ends, but you can call yourself a cosmologist as soon as you're doing research in cosmology. And some people do internships also during their bachelor's already. They join a research group and start working on cosmology during their bachelor's, which is great. And then we get a lot of really valuable contributions coming from bachelor students doing summer internships, for an example. So yeah, that's a long answer. The short version is it took me about 8 years before I would call myself, let's say 6, 7 years before I started calling myself a cosmologist. But that was an ongoing process. There's a comment from Prathia. I see there's a few in between, but comment from Prathia. You should do one stream where you defend your thesis from chat while we do the best to ask hard questions. Yeah, so I already did that. Like, I already did my PhD Viva. I did my defense, and it's very interesting to see how PhD defenses or the Vivas work in different countries. Like, every country has their regulations. Just this week, a few days ago, I attended a friend's Viva here in Finland, and it was very different to what I experienced in Germany. But also, it was just really nice to see that. Also, I love going to people's PhD Vivas because you get to see the culmination of years of work, and it's really cool. But during my PhD Viva, there was a public defense, so I gave a 30-minute presentation that was open to everybody, and it was supposed to be understandable to everyone. And then the general public was kicked out of the room to go do whatever they wanted to do for 2 hours, and I was left alone with my panel of 4 judges who had 20 minutes each to ask me anything they wanted about physics, not just about my thesis, because Germany, well, the idea was you were getting a degree in physics, therefore you should be able to answer any physics questions. That was absolutely terrifying, but it was done. So yes, I already defended my thesis against the panel of experts. And we could do another one where I defend my thesis here to you all, and you can all ask me questions as difficult as you want. I'd be up for that. I'd have to reread my thesis because it's been a few years. But to be fair, my thesis was basically on perturbation theory and cosmology, which, as you might remember, was the topic of Cup of Cosmology 2 weeks ago, where I did a 1.5-hour interactive discussion about perturbation theory. So I feel like I already kind of defended my PhD to you all then. But yes, I'm happy if people want me to do, like, let's stage a PhD defense here on Cup of Cosmology. I can do that. I can reread my PhD and do, like, ask me questions. But yes, happy to do that. And you always ask me questions anyway, so it's kind of like a weekly defense, except you guys are all, you folks are all lovely, and you don't ask you ask me tough questions. I was about to say you don't ask me tough questions, but you do, especially you, Prath. You ask me tough questions, like, what if we had a second dimension of time, or what do white holes have Hawking evaporation? And some of you do ask me really tough questions, but you all are lovely. Okay. So more questions, more comments. Again, for anyone who's just joining, this is an interactive stream. There is no topic today, which means this is just me rambling about physics, about cosmology, about science, about academia. You can ask me anything you want, and I will do my best to try to answer these questions. So feel free to ask anything. I will try to answer all of the questions in the chat. Somewhat coherently, somewhat following some type of train of thought, but we jump through questions. So we jump about how our minds hop about. There was just a quick comment from Scott. Has it finally cooled down? It has. It has cooled down. It is a very pleasant 16 degrees Celsius outside, which is lovely. And it has been raining the whole weekend. I think it's either tonight or tomorrow night that we're dropping down to 10 degrees because Finland doesn't know how summer works. And I love it. I am here for a 10-degree night with rain. Absolutely, bring it on. Yes, it has definitely cooled down. Also, 2 weeks ago when I was complaining about it being ridiculously hot, it wasn't actually the hot. I was coming down with a bug, and that made me have a hot flush. So when I was complaining in the stream 2 weeks ago, like, oh my God, it's so hot, actually wasn't just the heat at play there. That was also me coming down with a bug. Okay. Yeah, it's always people defending their PhD and never using them for attack, right? I think the best defense is an offense. We should be allowed to go on the attack. And then there's the fact that when you defend your PhD in Finland, you can get a PhD sword. Well, you get it. You get permission to have it, but you still have to pay for it. There's a couple €100. But you get a sword, and it's like a formal sword that you can carry at formal events. So I feel like, PhD should come. PhD defenses should come with a sword fight. We were joking, the person who defended this week, because here in Finland there's an opponent. So rather than a panel of judges, you call in one expert who can interrogate you for as long as this expert wants about your thesis. And usually you get someone who's worked on really similar topics. And the way it works here is there's this first, the candidate gives the person defending gives a 15-minute talk, 15-20 minutes. Then the opponent puts the thesis in perspective of the general field, what the accomplishments of the thesis, and reflects on the contribution to the field. And then the opponent and the person defending have kind of this conversation that is an interrogation. The one this week was done really nicely. It felt more like a conversation among experts. But they were joking afterwards that they wanted to stage a fist fight because it would be more dramatic. They didn't, to my knowledge. I left the evening before the celebrations finished, but to my knowledge, they did not in fact stage a fist fight. But yes, why are we always defending our PhD and not attacking? Right? You get a sword. You get a sword that you can carry around. You actually get this like official fancy. Well, you get permission to get this official fancy PhD sword. There's also a funny hat. You get like the PhD hats. But yes, you can get a sword if you defend your PhD in Finland. You can get a PhD sword, and then at formal events, some people have their sword. But yes, a cosmology PhD sword has to be made of meteorite iron. Yeah, kind of like what Sokka did in Avatar, make a sword of a meteorite. That would be very cool. Not sure how durable it would be, because it's not exact. Meteorites are not in general good for iron. Like it's a soft metal, but you can make a good sword out of it. It would be fun. Okay, going back to more questions. There was a question that I saw contained the word CMB quite close to the top that I still wanted to get to. I got distracted by other questions. Question from John. I was wondering about primordial black holes. I do too frequently. I wonder about primordial black holes. If they're embedded in a charged plasma prior to the CMB, would they be likely to become charged black holes? Love this question. Okay, so primordial black holes are black holes that form in the very early universe. Now, generally, when we think of a black hole, we think of a star that has reached the end of its lifetime. And I'm sorry, there's just a comment here that someone lost his nose in a sword fight, and I'm amused at the slightly randomness of that comment. Yes. Okay, so when we think of a black hole, we tend to think of a star that has reached the end of its lifetime and has collapsed. Black hole is a region of space-time that is so dense that nothing can escape, not even light. You'd have to travel faster than light in a vacuum to escape a black hole. As far as we know, nothing can travel faster than light in a vacuum. Therefore, nothing can escape the gravitational pull of a black hole. Most black holes that we found, that we think of, are black holes that are stars that reach the end of their lifetime. They collapse due to the gravitational force, and what's left behind is a chunk, a core of the star, of the dead star. They explode as a supernova, and they leave behind this core, and this core is what we call a black hole. However, there are also primordial black holes. So primordial black holes are black holes that would form in the really, really, really early universe. These would be when you have regions of the universe that are really, really dense, like you have a perturbation, as we saw a couple of weeks ago. So you have a region of the universe that is over-dense. This can be dense enough that it can directly collapse to form a black hole without going through all of the star formation process. So this means that these stars could form really, really early in the history of the universe. We're thinking about, just after the end of inflation. So if we go to our usual figure of the history of the universe, let me just bring up the history of the universe. It should be this one of these two. This one here. So this is our standard picture of the history of the universe. And when we're talking about primordial black holes, we're talking about ones that form just after the end of inflation. So after this exponential growth in the early universe. Now, these are primordial black holes. They're a hypothetical thing. We have not found primordial black holes yet. We're not sure if primordial black holes do actually exist, but they would have some pretty cool properties if they do exist. One of them being that they've been around for so long that they would have had time to grow more than other black holes that are formed after stellar evolution, which means we would have like these bigger black holes that could maintain traces of the early universe. Now, the question that John actually asks is, if they're embedded in a charged plasma prior to the CMB, would they be likely to become charged black holes? And this is a very cool question. So when we're talking about the early universe, we do think of the universe as being full of this plasma where we have kind of quarks and gluons, and they're forming this plasma. But if we think that primordial black hole and this plasma can or cannot be charged depending on the point in the history of the universe. But when we're talking about primordial black holes, we're really talking about ones that form right after inflation, just as particles are coming together, just as particles are forming, which means these primordial black holes will kind of be formed at the same time or even before this plasma was formed. They really are just regions of space-time that are so dense, they collapse. So they form and really at the same time as this plasma is like forming, or even before the plasma forms, before the first particles appear, depending on how particles appear in the early universe, which is an open question. I know I put it as a prompt, it is an open question. So if they're embedded in this plasma, would they be likely to become charged black holes? They could be. So we know that a lot of black holes have spin, and they can have a charge as well. And if black holes have a charge, it just changes the way we measure them. It doesn't really change much about the black holes, it just changes one of the things we can measure about them. So primordial black holes could be charged, but generally, in most pictures, primordial black holes would form before the overall quark-gluon plasma in the universe. However, there is the very cool thing that, because you specifically asked like prior to the CMB, prior to the cosmic microwave background radiation, so we can come back to that. I'll just see a comment here I'm going to go to some comments and then come back to this. We have some comments here from Pratt. Speaking of charged black holes, where can I learn more in depth about them? They are so under-discussed compared to other kinds of black holes. Yes, I don't have a good reference off the top of my mind, but I will look for one. Because charged black holes it's a lot easier to study non-charged black holes, because it's just a little bit easier. So we don't really discuss charged black holes as much. I don't have a good reference off the top of my head, but I'll see if I can find one for you. I'll see if I can find a reference here. How can a black hole be charged if charge is carried by photons and photons cannot escape the black hole to carry the charge? Excellent question here, David. Now, the idea is, when we think of a star that reaches the end of its lifetime and collapses, the star itself could have a charge based on the matter contained. So when the black hole collapses, this is a property that is not completely lost. It could be a property that the black hole still maintains, the same as it could maintain the spin of the star when it collapsed. When we're talking about primordial black holes, can primordial black holes actually be charged? Yes, by the same principle. You can also have fun things if you can have photons kind of trapped in the accretion disk of the primordial black holes, and this can also give it a charge. Let me just check something here, because I am now doubting primordial black holes charge. So I am doing what every scientist does when we doubt, and I am asking Google, because yes, that is now a question that I'm debating. So yes, primordial black holes could indeed hold charge, apparently, but it is not the general idea. So usually we think of primordial black holes as being neutral, as being not charged, but you can have kind of this charge in a black hole formed by a star, and we can try to apply this also to primordial black holes. So technically, yes, you could have a charge in a primordial black hole, but it is not the usual scenario, because they are formed prior to the plasma, so then they don't really have a charge at the time when they're formed. You can talk about a different type of charge, which is a colored charge, which black holes can have, but then that's a very technical point. But the comment I did want to make, if primordial black holes exist, they were formed prior to the CMB. So finding them will give us insight into the universe even before the CMB, before the cosmic microwave background radiation. Just as a reminder for anyone who hasn't seen it today, took almost 25 minutes today. The cosmic microwave background radiation is the oldest light in the universe. It is a snapshot of what the universe looked like 380,000 years after the end of inflation. In the early universe, there were protons, electrons, and photons, and dark matter doing its own thing. As all of these three were bumping into each other constantly, as the universe cooled down, protons and electrons could combine together to form neutral hydrogen, and the photons at that point, the particles of light, broke away. They've traveled freely throughout the universe since then, and today they make up the cosmic microwave background radiation, the background radiation that we can see anywhere we look in the universe, in the microwave range of the electromagnetic spectrum. Now, this gives us a snapshot of the universe 380,000 years after the end of inflation. If primordial black holes formed, they could have been formed at the end of inflation, so 380,000 years prior to the CMB. So measuring primordial black holes will give us a snapshot of the universe really, really early times before the CMB. And there is a cool thing that if primordial black holes exist, they would have matter falling in on them. This happens to every black hole. Black hole will accrete matter, will absorb matter that is close enough, because it is a big gravitational object. So anything that gets close enough will feel the gravitational pull of the primordial black hole and will fall into the black hole. This can lead to an accretion disk. An accretion disk is basically, if you have your black hole, here you would have this disk of matter around the black hole. So when you look at it in this direction, you kind of have your black hole here and a disk surrounding it. This is a disk of matter. As this matter falls around the black hole, it can spiral, it can charge, it can heat up, it can have friction, so you will get this kind of visible disk around the black hole. The visible disk here is this part here, the black hole you can't see, but we can see this accretion disk around it. So if we have primordial black holes, this accretion disk is producing energy. And this type of energy can actually affect the CMB, specifically the direction in which the CMB photons propagate. No, sorry, not the polarization. So when we look at the CMB, usually we look at this map here, which is the changes in temperature. So the tiny, tiny, tiny differences in temperature of these photons. But there's something else we can do, which is look for tiny, tiny, tiny differences in the spectrum. Now, the CMB emits like a black body. This means it emits every frequency of light. This is, in fact, the most perfect black body we have ever seen. However, there could be tiny, tiny, tiny differences to this black body. This is what is known as spectral distortions. And primordial black holes would produce spectral distortions in the CMB. This means if we can ever get a mission to measure CMB spectral distortion, so these tiny changes in the frequency spectrum that photons are emitted in the CMB, we could actually find hints of primordial black holes, because if primordial black holes have this accretion disk, this accretion disk would release energy that would affect the distortions of the CMB. Currently, the only spectral distortion mission we've had was many, many years ago, 1995, together with Kobe, the first mission to measure these photon differences. And there was feeders on board the mission, Kobe feeders. Feeders measured the spectral distortions or put a bound saying they can't be bigger than 10 to the minus 5. The ones predicted from primordial black holes would be of the order of 10 to the minus 6, or sorry, 10 to the minus 8 or 10 to the minus 9. So we need a future mission. Spectral distortions is a topic I have done streams on in the past, and I can do another stream on if people are interested. It's a very cool topic. But I'm just going to leave it at that, because the question was not about spectral distortions in any way. It was about charged primordial black holes. So generally, we don't think of primordial black holes as being charged, but they can still affect the CMB through spectral distortions, and this is something we might be able to measure in the future. So primordial black holes are cool, CMB is cool, and spectral distortions are cool, and we can tie all three of those together. So that was a great question. I know I went a bit further in different directions to what the questions actually were, but that was a fun connection to throw in, going through primordial black holes. I see there was a follow-up from John following up to this question that I've only just read here. Related to primordial black holes, if they can be charged, I was wondering if the mass difference between electrons and protons might cause them to shed kinetic energy and fall in at different rates. That's an interesting idea here. So the mass difference between electrons and protons. So again, we're talking about primordial black holes that are formed prior to the plasma. So when the primordial black holes were formed, there wasn't really this big difference. So there wasn't anything in the universe other than space-time and some quantum fields. So there weren't protons and electrons at the time when these formed. However, I'm guessing you're talking about things falling in there. Now, the problem here is most protons and electrons are combined together into atoms. And in order to separate these, you need a huge amount of energy. So the force that is holding these together is the strong force. And the strong force is the strongest of all forces. The strong force glues things together, it keeps things as they are. So gravity is the weakest of all the forces. So gravity is not enough to overcome this and separate protons and electrons. So if you have an atom falling into a black hole, you're not going to pull this atom apart due to the gravitational present. If you have a big object, you can get spaghettification, but you will not be able to rip atoms apart. Atoms cannot get spaghettified by a gravitational force because the gravitational force is not strong enough to do that. So if you have protons and electrons falling in separately, they will fall in at slightly differently because of the mass, although at some point they reach the maximum velocity. But if you have atoms, these are not going to be pulled apart by the black holes. I'm not completely sure if that answers your question, John. I hope so. But if not, let me know, and I will try to answer it a different way. But yes, so that's a very cool questions. I like the questions about primordial black holes. Oh wow, this is an odd tea. This is a tea that's been sat in my tea box for about 2 years. It is rooibos, rhubarb, strawberry, and cream. The rhubarb and the strawberry work. The creamy flavour to the tea is interesting. There's a reason this has been sat in my cupboard for 2 weeks, but I forgot to buy my caffeine-free tea, and this was the only caffeine-free tea in the house. Oh, that is weird. Yeah, that tea might sit there. Okay, more questions. Let's see. There was we talked about defending the PhD. Okay, more comments here. Defending the PhD, we should have a sword. You just roll up the diploma and use the cardboard roller. Yeah, when you're defending your PhD, you should be able to just roll up a copy of your thesis and bonk people with it. Also depends on the thesis, because some theses are pretty big, you know. You can just bring the book and bonk people with it. My PhD thesis was 300 pages, and that's expensive to print, incidentally. And the university did not reimburse that in Spain. And in Germany, sorry. So it's like you pay money to print out this thing, and it's like a big book to just bonk people with. Yeah, we should be allowed to do that. If people ask difficult questions, we should just be able to hit them on the head with the defense. You know, there's also usually the thing where in every country the audience can ask questions as well. Like when I did my presentation in Germany, at the end of those 30 minutes, anyone in the room could ask questions. And maybe I think one or two people asked questions, but they were very friendly. The one that was here in Helsinki the other day, after the opponent has asked all their questions, the audience gets a chance to ask questions, but it's kind of unofficially agreed upon that nobody does. They barely gave time. They were just like, are there questions from the audience? No, okay, let's close the session. Because it's kind of expected that you're not going to interrogate the PhD student as well. But yes, I think we should have the option that if someone asks a tough question during your PhD defense, you should just be able to hit them with your thesis or with the sword, which you can get in Finland when you defend. I see there's some very interesting questions that I want to get to. So let me just go through the random questions. Okay, I think we covered all of those. So I see there's a lot of very cool questions because I took quite a while to answer one of them. So no more questions have come up. But there was a very nice question here from Alok of, can you discuss how vibrant and promising the field of cosmology is expected to be in the next few years? And I love this question. I love this question. Before getting to this, follow up from John. Thanks for the great answer, but to clarify, I was wondering about electrons and protons falling in differently because before recombination, they wouldn't be combined in atoms. Okay, yes, so you're talking about the time after primordial black holes have formed and before the CMB. At that point, when you have protons and electrons, can they fall in? So generally, we talk about there being protons and electrons and photons, and this is accurate. And they're constantly bumping into each other. This actually means that they're kind of behaving as a big gas. They're behaving as like one fluid. And it is quite hard to separate them at this point, even with the gravitational force. If a proton and an electron are close enough to fall into a primordial black hole, they will fall into the primordial black hole, regardless of the difference in mass between the proton and the electron, which is only a factor 2. So they would still be able, not factor 2, sorry, factor 200. So they would still be able to fall in together because they're kind of caught up in this gas cloud. So it gets sucked up together. I think the difference in mass between the two objects is not really that big to make a difference in the time they fall in, and therefore it would not show up in the CMB. But yes, it does make sense that between the primordial black holes potentially forming and the time of the CMB, you have this gas cloud of the protons, the electrons, and the photons, and these all can fall into the primordial black hole, and they would fall in at approximately the same time, despite the tiny mass difference here. Who is the audience? General people or students from other faculties or your peers? So officially, in every country that I've worked in, PhD fivers are open to literally anybody. So anyone from the street can walk into a PhD viva. The idea is that this should be open and public. In Germany, when there's the private part of the examination, obviously everyone leaves the room except the person defending and the jury. In Finland, it's open to everyone. Like literally anyone is allowed to attend. These events are announced publicly. In some countries, like Germany, there's then an added regulation that you kind of need to be a physicist to be able to ask questions. Like, I think the rules are actually that only someone with a PhD themselves is allowed to ask questions because, Germany and hierarchies. But these vivas, these PhD defenses, are usually open to the general public because it should be a public event. Now, often the audience is people from your group, people from the broader group, friends and family that you might want to invite. People usually invite friends and families to this. I feel like I will go to any PhD defense if it's a topic that I know vaguely something about, or if it's somebody who I know, just because it's good to go there to these events. In mine, there were people from my faculty, people from the broader Department of Physics, there were friends, there were family members. So it's really open to whoever you want. It's a big deal, so it makes sense that you invite people. Like, personally, I probably won't go to a PhD defense in biology unless I knew the person defending. But if it's in a topic about physics that I know even the slightest bit about, I will try to go to it. Also, because there's usually free cake afterwards, and that's a good reason. So yes, PhDs defenses are usually open to anyone who wants to go, but the target audience of the presentation is anyone in physics. Like, convince other physicists that what you've done matters to cosmology or to whatever topic you're working on. So when I gave my talk, the general idea was my presentation should be accessible or understandable to anyone who has a bachelor's degree in physics. And then usually you give a broad introduction, is also because at that point you don't want to give a technical presentation. That's what your thesis is for. That presentation is more about putting your work in the context of the broader field, like why you've done what you've done, why it mattered to you, and that's what you're supposed to do, what you're supposed to convey in these PhD defenses. Okay, so I wanted to answer the question from Marlock. Where was that good question? So somewhere up here. I lost the question. Can you discuss how vibrant and promising the field of cosmology is expected to be in the next few years? Yeah, so I think we're expecting quite a few cool things to happen in the next few years. The first one is we have a couple of ongoing missions trying to figure out what dark matter and dark energy is. So just to recap, the universe has three main ingredients: everything we see, everything we're accustomed to, everything from me to my slightly dodgy tea, to my plants, to the flies that are pestering me in here. All of this is normal matter. Normal matter only accounts for about 5% of the energy budget of the observable universe. There's another 26.2% in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but does not interact electromagnetically. So we cannot see dark matter because it does not emit light, it does not absorb light. As far as light is concerned, dark matter is not there. Hey, James, joining from a plane. I think you're the first person who's watched Cup of Cosmology in a plane. Welcome. Hopefully you're having a good flight. Enjoy your flight. I'm glad you're watching Cup of Cosmology from a plane. You're getting a bit closer to space than people watching on Earth. Small difference, but you are closer to space. Good place to watch Cup of Cosmology. The remaining 70% of the energy budget of the observable universe is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy. We currently have a couple of missions, space-based, ground-based, trying to figure out dark matter and dark energy. For an example, the Dark Energy Spectroscopic Instrument, turned on about 2 years ago, is a ground-based telescope trying to measure 40 million galaxies. They already measured about 6 million in the first year, and in their first data release, they found hints of dark energy doing stuff we didn't expect it to do. We are expecting more data from DESI, from the Dark Energy Spectroscopic Instrument, in the coming months, in the coming years, and that's going to give us a lot of information about dark energy. Then we have Euclid. Euclid is a space-based mission that launched over a year ago by now, July last year, and it is a mission that is trying to figure out dark matter and dark energy and the structure of the universe. From what I've heard, we're going to get data sooner than we expected for Euclid. So there is going to be data, like actual science results, within the next year or two, and that's going to be super exciting. Then we're also turning on the next generation of CMB missions. So pushing the polarization and the temperature measurements of the CMB. So this map that we have here is already incredibly precise, but this is for temperature anisotropies. We can also do a similar map for the polarization. So the direction these photons are vibrating in. That is also something we expect to get more precision on over the next few years. And 10 years from now, or 12 years from now, we're going to launch a space-based gravitational wave mission called LISA, the Laser Interferometer Space Antenna, which is hoping to measure gravitational waves from the first fraction of a second of the universe, which is very cool. So those are all things that are upcoming and that are ongoing with cosmology. And I think we're entering the age of data cosmology. So since we got the first measurements from Planck in 2013, since we got the first really detailed version of this map, we've been in what is known as the era of precision cosmology, where we're able to get these numbers in the pie chart with this level of precision, where we don't just say 5% normal matter, we can say 4.9. It's not just 25% dark matter, it's 26.2. This is precision cosmology. Now we are entering an era where we're going to get so much information from galaxy surveys, from Euclid, from DISY, from CMB missions, that it's really the age of big data cosmology, where Euclid is expected to produce terabytes of data every month. It's producing an insane amount of data. Having access to this volume of information about the universe, we are the first people to do this. We are the first humans to have this amount of data about the universe. So this means we're going to learn more about our models. We're going to push our precision in every aspect. We might find things we don't expect, which is where the fun starts. So I think there's a lot to look forward to in cosmology in the next few years. There's a lot of missions bringing us data. There's a lot going on. And I think it's going to be exciting. I think the next 10 years are going to give us really interesting results for cosmology. I think we're going to get more information about dark matter. We're going to get more information about dark energy. We might figure out the Hubble tension, so why the universe expands differently depending how we ask the question. So the universe should expand the same, right? But when we try to measure how quickly the universe is expanding, depending on the measurement technique we use, there are different results. And these results are in tension with each other. They don't completely agree. This is the thing that I have a hot drink, I'm going to drink it even if it doesn't taste good. I can see that. I'll drink it. I'm not going to enjoy it, but I'll drink it. So yeah, we are getting a huge amount of information. We are going to get more information about this discrepancy of the Hubble tension. I think we're going to solve the Hubble tension in the next 10 years, optimistically. So I think there's a lot to look forward to in the universe, in cosmology, in the next 10, 15 years. How many years did you ask in your question? The question from Alok here was expected in the next few years. Okay, I went to 10, 15. But yeah, in the next 10 years, I think we're going to solve the Hubble tension. We're going to learn more about dark matter. We're going to learn more about dark energy. And in the next 15 years, we're going to figure out early universe gravitational waves. We're not figure out, but we're going to measure early universe gravitational waves. And I think all of these are really cool things and things to look forward to in cosmology. There's a lot happening, a lot of cool stuff happening. Okay, going back to more questions. There's a question from Shwani earlier where we talked about swords and stuff. There's a question from Shwani. Is it possible for humans to be quantum entangled like quantum entangled particles? If so, could this entanglement connect us to different universes? This is a very nice question. And so when we talk about entanglement, we're talking about usually particles that have shared properties. So for an example, I can prepare two electrons, one that has spin up, one that has spin down, and I can prepare these in a way that is entangled. So one of them will definitely be spin up, one of them will definitely be spin down. Spin is just a quantum property of electrons. It doesn't mean it's actually spinning. It's just a property we give it, and we just call it up and down. Now, if I prepare these electrons with up and down and split them, no matter where they are in the universe, as soon as you measure one to be up, you know the other one is down. Before measuring, we have the superposition principle. Both are up and down. We don't know which is which. As soon as you measure this one as being up, you know for sure this one is being down. You collapse the wave function. This means that even if these things are light years apart, as soon as you measure this one as being up, whatever you do to that one, it's going to be down. It collapsed to being down. Before you make the measurement, they're both. As soon as you make the measurement on one, they both collapse. This is quantum entanglement. It's also called spooky action at a distance, because how does this one tell this one that the measurement has been made? The idea is it doesn't need to tell it because this information exists in both places, and it's when you make the measurement that things collapse. Now, quantum entanglement gets harder when you move to things that are not particles. So we know that humans are not quantum. I cannot be simultaneously here and here. I'm in one position. We are not quantum. Do not fulfill the laws of quantum mechanics. We fulfill the laws of classical mechanics. This means that it's quite hard to entangle things when you get bigger and bigger and bigger. Scientists have worked on trying to entangle Bose-Einstein condensates, which are something that is like bigger than a particle but not quite an atom. It's kind of like where you shove particles together in a weird configuration in a super cool region, and you get this kind of Bose-Einstein condensate. People are trying to entangle these, and it is really difficult. They have managed to entangle Bose-Einstein condensates, but it's not easy. And then trying to entangle atoms gets even harder. So the larger the object, the harder it is to entangle it from our perspective. So if a human was entangled with something else, you'd only be entangled with like one property. So which property are we entangling here? Let's say hypothetically we entangle something like, eye color. This is something that is a genetic trait. It is something that is tied into our DNA. Perhaps you can entangle the DNA strands, but it becomes very, very hard to talk about entangled objects when we move to the classical picture, because in the classical framework, things are not entangled. Things are what they are. If you know the initial conditions, you can predict the outcome. If I drop this pen, I know exactly where it's going to fall, or you can calculate where it's going to fall if you knew all of the conditions. In the quantum world, before you make the measurement on these two entangled electrons, there is no way to predict which is up and which is down, because they are both until you make the measurement. When you make the measurement, they collapse. One is up, one is down. Until you make the measurement, both are both. But they both are both, but they are entangled. So when you measure one, you get the other one as well. Bigger objects do not obey the laws of quantum physics. They're deterministic. If you know the start, you know the end. There is no randomness. There is no chance. So it's quite hard to conceive of a human being entangled, because humans are just big. If you want to break it down, like, could our individual particles that make up our atoms be entangled? Then it gets a lot more complicated, and then you'd need a mechanism to entangle them. And I'm not sure if having like one particle or one of your electrons entangled with another electron would gain you anything. So yes, entanglement we talk about entanglement when we're talking about quantum things. Entanglement in the comment here from Pathfinder, entanglement in the context of spin is simply conservation of angular momentum between the two particles. Well, is not necessarily conservation of angular momentum, because when we talk about spin, it's not really angular momentum. We call it spin because it's a quantum property, but it is not necessarily the same as something spinning. Keeping with this topic, I know there were other really cool questions. I am saying that cleaning products cannot clean at the quantum level. Indeed, pet peeve of mine. There was an ad in Spain for quantum finish. It cleans products at the quantum level. I am still not over this. It has been 15 years. More than 15 years, I am still not over this ad. You do not clean things at the quantum level. That's not how it works. A comment from Perthia, my guess is that the mirroring of how superposition changes is locked in when the particles are entangled. That guarantees that the superposition will collapse to opposite states. Yeah, it's basically contained in the waveform. So in the mathematical description of these two particles, this entanglement is there. It is contained there. Hey, Fortanine, great to see you again. I know you always have very cool questions. Always good to see you as well. Comment from Guadav, I tried to build a cloud chamber today to detect cosmic rays but failed. Well, it's very cool that you tried. And these things sometimes go wrong. I would encourage you to try again. So a cloud chamber is an experiment you can build to actually see particles. So you basically put like a bit of an electric field, you put a gas that has specific properties, and the idea is when you set up a cloud chamber, if you have particles coming in from the atmosphere, like cosmic rays, you can actually see them leave traces in the cloud chamber. So cloud chamber is a very cool experiment that you can build yourselves. And it really allows you to see that particles are a thing because you can see the particle traces. And based on how the particles move throughout the cloud chamber, you can figure out what particles they are. It's something that is often done in an undergrad course, in an undergrad lab course of let's build a cloud chamber. I personally have never built one. I've wanted to for many years. I've seen other people build it, but I've never actually built one myself. But I know it's a bit tricky. Like the signs of it make sense, but there's a lot of tricky parts. So if you fail, don't worry. That happens. It's part of being a scientist. Sometimes our experiments don't work. I would encourage you to try again, make a cloud chamber because it is really, really cool thing to do. You have 30 kilos of dry ice and no clue what to do with it. Dry ice is so fun. You can make smoke. If you're a theatre person, you can make smoke. If you like the drama, you can just make smoke with dry ice. Dry ice is fun. You can get up to a lot of shenanigans with dry ice. But I would encourage you to try to make a cloud chamber again because they're great fun. Or just find what can I like Google what can I do with dry ice, and you'll find a lot of fun things to do with dry ice. It's really a fun thing. Next stream, I build a cloud chamber live. See, I'm a theoretical physicist. I'm not good at well, I'm good at building some things, not other things. Like I can assemble furniture. I can build a plant wall. I can do things with my hands. I'm not completely useless in that sense, but building an experiment like a cloud chamber, I'm not sure if I'd succeed, especially with the pressure of doing it live. This is one of those things that see, this is why I normally have tea. This is one of those things that when people watch you always do worse. Like I'm a good coder. If someone's watching me, I forget how to type. You know, I forget how my keyboard works. It's the thing that you can't do things when people are watching you. So no, I'm not going to build a cloud chamber live because I will absolutely mess it up. But one experiment we could do live is measuring the speed of light with a microwave. You just need a microwave and a bar of chocolate, and you can measure the speed of light. The problem there is like bringing my microwave here. So yeah, a cloud chamber is this kind of experiment that has, it looks like it's nebulous. It looks like it's got a cloud in it. So you put a black surface underneath, you put a specific gas on top. It's encased in glass. The gas you can do with like dry ice. And what it does is it leaves marks, like the gas gets kind of charged or leaves visible lines when particles come in. So a cloud chamber is this experiment that you can use to really see how many particles are just bombing about all the time. You can build this kind of chamber that's filled with gas, and it looks like particle. And anytime a particle goes through it, you can see it. Some particles might bend around because they're charged particles. Some particles go through quickly. I mean, a cloud chamber is one of the first ways that people actually saw particles or measured particles, because it's something that is relatively, from a physics perspective, it's relatively straightforward. And it's something that just really allows you to study particles. There is actually one in my campus. There's people just put a cloud chamber in one of the hallways, and you can just walk past and look at the cloud chamber in my university. It's very cool. I don't have a photo at hand of a cloud chamber to flash up, but we could talk more about that in another stream if people are interested. Like really go into detail about how people have measured different particles over the years, because measuring particles in a cloud chamber is really fun, and it's something that you all can build. You can find instructions online. You can try to build it. All of the material is readily available, which is like your own backyard particle detector. It's pretty cool. It's pretty cool. And if people like building them, I really encourage you to try to build one. It is fun. So I know I've missed some questions. Comment here from Sophia. I had a chemistry teacher in high school who tried to do experiments in class every week to demonstrate stuff. And I think one or two of them succeeded. Yeah, it's great fun. I love teachers who do that. That's really cool. Trying to do these experiments, trying to build things, trying to poke at things. I remember I had a biology teacher who did that, but there's a class of human anatomy, an optional class of human anatomy that I took in the last years of my high school, so at the ages of 17 and 18. And this teacher was once a week was like, let's dissect something. And we would dissect different organs. Not as fun as building a cloud chamber, but also very curious. Yes, very, very fun. Yes, I love it when teachers do hands-on experiments like let's build stuff, let's do stuff. Yeah, I had a physics professor who did a less kind of reasonable experiment at some point, which was highly funny and stuck in my mind. Just a comment from Guadalupe here that people won prizes using cloud chambers. Yeah, there was Nobel prizes with cloud chambers. It's very cool. I know there's a bunch of questions I haven't got to, and we're going on a tangent now, but I'm going to go down this tangent and then come back to the questions. Yeah, we can do the PhD defense with dry ice theatrics. Yeah, just put on a show. You know, if we're going to do it, we're going to do theatrics. We are the theatre kids. They know what to do with dry ice. Yeah, in my high school, during my physics classes when I was 17 or 18, I had a teacher who had basically run out of cares about the world. One day he brought in a pack of cigarettes and a 20-euro note, and he did a test where he would get the students to put your hand out, and he'd put the 20-euro note on top, and then he'd burn it with a cigarette. And the idea was, if you kept your hand there until the banknote started to get smoke, you could keep it. So if the banknote started to burn in any way and you still had your hand there, you could keep the 20 euros. So of course, all of the teenagers in the class were like, oh, I'm going to win 20 euros. And this teacher would just light his cigarette and put it on the students' hands with the banknote on top. This is very much not like health and safety approved. But your hand heats up to a point that you have to move it before the banknote burns. And the reason for this is the different ways that different materials conduct heat. So the banknote doesn't get hot, but your hand does, because your hand is there, it conducts heat better than the banknote. So then people's hands will get hot before the banknote would. So nobody managed it, because you will pull your hand back when it gets hot, and the banknote is still not a scratch, not a bit of smoke on it. You know, it has been 20 years since I saw this, or 17 years since I saw this done. I still remember the physics behind it. I do not think that was a way of showing us, like, this teacher did not have approval to do this experiment in class, but it was really fun and memorable. And, 17 years later, I remember the physics he taught us. Point being, teachers who do experiments are very cool, especially if those experiments have been approved, like health and safety wise. But even so, I think teaching by showing is a great way to explain things. Yeah, those kids just weren't tough enough. That's what all the kids thought. The kids thought, these teenagers were like, I'm going to win 20 euros, ha ha ha, easy money. No one succeeded. All the tough guys in class tried, none succeeded. Which was also very funny, because then we were laughing at the tough guys. Yeah, this teacher definitely got us all very engaged. Really don't think what he did would have been approved by any board. But it was fun. It was very funny. It was very memorable, at least. Okay, let's go back to the questions, because we are 1 hour in, and I think I've answered like 4 questions, because we've gone on a lot of tangents and answered things really in depth today. But there were more questions that I wanted to get to. Let's go back to the questions. We just did the one about humans being entangled or not. There's a question from Edward some time ago. Why did the universe let me make a homemade meat fest pizza to then let me drop it face down on the kitchen floor? The universe is a cruel mistress. I'm sorry that you dropped your pizza. That sounds like a good pizza. I realize that was not an actual question. But yes, the actual answer is entropy. It's easier to drop a pizza than to carry a pizza. Blame entropy if you drop your pizza. Also, I'm sorry, you dropped your pizza. That doesn't sound nice for you, but it is quite amusing. Okay, we got through the charged black holes. There was a question from Prath about dark matter about half an hour ago, but I was digressing. I was onto tangents about dry ice. So dark matter formed at the beginning of the universe. Then why did hyperinflation stop? And why hasn't the expansion of the universe been accelerating since then? All very good questions. So we don't know completely when dark matter formed in the history of the universe. We think it was just after inflation. So after inflation, there is this time, if I bring up my history of the universe figure here, you can see we have on the top, we have cosmic inflation, and then particles form. This is when particles appeared in the universe. This is also when dark matter appeared in the universe. Generally, one idea that we have is the field, the energy that caused the initial inflation of the universe. When inflation stopped, that energy had to go somewhere, and that energy went into producing the first particles and the dark matter in the early universe. This is one idea of how dark matter and particles were formed. There are other ideas. There are many different production mechanisms for dark matter, and we don't yet know which is the correct one, but one idea is that inflation ended and this kind of heated up the universe. Why did hyperinflation stop? So in order for inflation to happen, you need certain conditions to be fulfilled. One of them is you basically need a lot of energy to be able to drive this accelerated expansion. And at some point, the universe grows so much that you basically don't have enough energy to continue this accelerated expansion. And so inflation naturally stops. Generally, when we talk about inflation, we think about it as like a ball rolling down a hill into a valley. So you might think of this is your potential energy. You can see questions from previous streams here if you can read sideways. So this is like your potential energy. This is time. So you start up here. As you roll down this potential energy, this is when inflation happens, and then you reach the bottom and you just kind of stop. This is exaggerated. This is very much not a realistic picture, but this is an idea for inflation. So inflation basically stops when it runs out of the energy to continue fueling inflation. Dark matter, generally in most mechanisms, dark matter is produced after the end of inflation, but there are some mechanisms that produce dark matter during inflation or even before inflation. As to why hasn't the expansion of the universe been accelerating since then? So this is, again, map of the history of the universe. Now, the general idea here is that the universe contains a lot of gravity, a lot of matter. This is going to cause a gravitational field. So you have a battle between the universe going outwards due to inflation. When inflation ends, there's this residue energy that keeps pushing it outwards. Like the exponential expansion has ended, but there's still this kind of residue motion. But gravity is going to pull things inwards. So if we didn't have dark energy, the general picture would be that at some point, dark matter and normal matter, the amount of matter in the universe would win. And after this initial inflation, it would gradually slow down, stop, and then collapse upon itself again. However, at some point, dark energy became the dominant energy source in the universe, or the dominant component in the universe, and this reignited this accelerated expansion. So we had this initial inflation, then it started slowing down a bit because of gravity, and then it sped up. It never reached the point where it went inwards. It's just this expansion slowed down and went up again. So it's just, and then dark energy pushed things outwards again. So I hope that answers your 3 questions there, Bruff. Don't know why I'm coughing so much today. One of those dry coughs that just persistent thing. This is why my inhaler is always next to me when I'm doing a live stream, because I do have asthma because of my long COVID. And sometimes I do need inhalers because of the coughing fit. So anytime I do a live stream, this is on the desk with me just in case. But I don't need it now. I just got something in my throat. Okay, so dark matter formed probably at the end of inflation. Inflation stopped because it ran out of energy, and the universe kind of stopped accelerating because of gravity, and then dark energy pushed things outwards. Okay, great questions. Keeping up with these good questions. There was another one, keeping with expansion. Then we'll go back to other questions. There were 2 questions about expansion together when I mentioned the Hubble constant. Question from Shawnee, do we have any theories of why the expansion of the universe has increased from dark energy? So dark energy pushes everything outwards. This is kind of like what dark energy does. It's its thing. And it's because of the fact that dark energy basically has negative pressure. So it pushes things outwards. It acts as a repelling force. So it basically acts as a repelling force. It's a repulsive energy that pushes things outwards. Our general idea is that dark energy is driving the accelerated expansion of the universe. We don't exactly know what dark energy is. So the underlying mechanism is something we're still trying to figure out. But there are a lot of ideas for dark energy. It could be a fifth force in the universe. It could be an energy field. It could be similar to inflation. And then we had a comment from Karma here of why does the universe expand in the first place, let alone accelerating, which is due to dark energy. So it expands in the first place because of this inflation era. So we start with something, we don't know what, because it's hard to talk about anything that happened before inflation. And then there was this period of exponential expansion, which we call inflation. After inflation ended, gravity kind of slows down the expansion, but not enough to bring it inwards. It slows it down. Then dark energy becomes the dominant component in the universe, and things push outwards again and accelerate again. And one of the biggest reasons we suspect there was this phase of exponential expansion in the early universe that we call inflation comes when we look at the cosmic microwave background radiation, the background light everywhere we look in the universe. Wherever you take this in the night sky, it is at approximately the same temperature. So there are these temperature differences of the order of 10 to the minus 5, so 1 part in 100,000. But overall, the CMB is at minus 270 degrees Celsius, 2.73 degrees Kelvin, minus 440 degrees Fahrenheit, I think it is. And it is this average temperature everywhere. And one question we can ask is, why is the CMB so uniform? Why is it at approximately the same temperature everywhere? And an answer to this is because before inflation, all of the things that we can see today were actually touching each other. They could exchange energy, they could exchange information, they could balance out. Then after inflation, this was stretched so much that it occupies the entire observable universe. So we add inflation to answer the question of why do different parts of the universe appear to have been talking to each other in the past. And one way we can answer this is with a period of inflation. Okay, so I answered the 3 questions together there. See if there's more comments here, no more related to this topic. I might need to rest my throat. It has already been an hour. Yeah, this is also one of the reasons why the streams used to be 1 hour. The last couple of weeks, they've been like 90 minutes, an hour and 20, an hour and 15. You know, I have fun chatting. There's still questions to answer. I'm going to keep going. Comment from Scott here. I bet you could do it. Scott, I encourage you to try it because this is not as easy as it sounds. Like, if you want to, so you take your hand, you put a banknote on top, try to set fire to it with whatever you want, and you will inevitably move your hand out before the banknote starts to get any marks on it, any simmering on it. I'm guessing this works with US dollars. You know, I know it worked with euros because of the material. I guess it works with different currencies as well. But you will move your hand first because your hand is going to start to burn. And at some point, no matter how good of a tolerance for pain you have, at some point, if your skin is burning, you are going to move your hand away. And the note will still not have any mark on it because of the way they conduct heat. So it's not a matter of being able to keep your hand there. I don't think anyone would be able to succeed at this test. You can try. Please don't sue me if you burn your hand trying this experiment. But if you're inclined, you're welcome to try it and see if you would do better than the teenagers did 17, 20 years ago when we did this experiment. Okay. Another comment from Prath about inflation. I will go back to the other questions I've missed in a minute. Sticking with inflation and dark energy. Is inflation equal everywhere, or do some parts expand more than others? This is a brilliant question, Prath. As always, very, very good question here. The answer is we don't know. So what we can say is that the patch that is our observable universe, inflation happened the same pretty much everywhere. But you could very feasibly come up with an idea where you have kind of patchy inflation, where this pocket of the universe experiences one type of inflation, this one another, this one another. The amount of inflation is different. The strength of inflation is different. And what this would lead to is what is known as the multiverse, where you could have, and I'm not talking about the multiverse in the Marvel context or in the sci-fi context where you can universe hop, but generally where you could have universes with different laws of physics. Because if inflation lasts a different amount of time, the universe might look different. If inflation is a bit stronger in some regions, this might affect the mass of particles. So oftentimes when people talk about the multiverse, one way to get to it is this idea that you could have patchy inflation, so different amounts of inflation or pockets where the universe inflated, where it didn't. Each of these pockets would result in a universe with different properties, with different characteristics. Which is very, very cool to think about. And some people say that if you believe in inflation, you have to believe in the multiverse, because when we talk about inflation, there is no way to guarantee that it happens the same everywhere in the universe at the same time. Actually, the first conference I went to as a master's student, was it as a PhD student, the first conference I went to as a PhD student where I gave a talk, we had often at conferences they invite a super important physicist or super well-known physicist to give a public outreach talk because it gives the conference more visibility in general. So this conference where I went to in Hamburg in Dizzy, the outreach talk was about inflation by Alan Guth, often considered to be one of the pioneers of the inflationary model. And I was there as a like 2 months into my PhD, very very early stage, and during his public presentation, he made the comment of, if you believe in inflation, you have to believe in the multiverse because you're going to have these different pockets of inflation, and this would generate the multiverse. And I disagreed with this comment. And the next day, I bumped into him over breakfast. No, not over breakfast, over like morning coffee. And I just out to him and I was like, hey, I disagreed with your comments. And he was like, who are you? Hi. And we had a super lovely conversation. And it really struck me because often we think, these super important physicists are, he's just like any guy. And we had a really fun conversation. And he actually listened to my perspective, which I thought was really cool because he didn't need to. It was really nice. We didn't reach a consensus. But yeah, there is this idea that some people think that if you believe in inflation, you cannot feasibly explain why inflation would be the same everywhere in the universe. And if it's not the same everywhere in the universe, you will naturally end up with the multiverse. Now, I'm still not sure where I sit on this debate in the many years since I had this conversation, but I can see why this reasoning of inflation leads to the thought of the multiverse. But in my mind, inflation is a way that we explain why our universe looks the way it does. And if there were other universes that look a different way, is not really relevant to our universe. And so I don't really see why we need to go down that path. So follow up here from Prath of how does inflation affect mass of particles? So if particles are produced by what is known as reheating, so reheating is an idea that after inflation ends, the field that pushed inflation, that caused inflation, this kind of quantum field, that energy needs to go somewhere. That energy could go into reheating the universe because during inflation, everything cools down a bit, and it would reheat the universe by forming the first particles. So then the properties of the particles depend on how much kind of energy is left over at the end of inflation in this idea of the inflaton reheating the universe and generating the particles. So then the mass or the charge or the properties of the particles are slightly related to the properties of inflation. So if you have different pockets of inflation with different amounts of inflation, you could feasibly end up with different particle physics, different standard model, different interactions between particles, and it would be via inflation. Again, at this point, we're getting into the very hypothetical. When we go to this early phase in the universe, everything gets very hypothetical. These are things that are very difficult to test, very difficult to confirm. It's like this whole conversation about the multiverse is not something we can actually test or prove or confirm because we are limited to the information in our own universe. Similarly, like the properties of inflation is something that is very difficult to pinpoint because we're talking about something so long ago that it's just very hard to get any information from what actually happened at this time. Okay, back to more questions. There are lots of very cool questions. I'm going to do quick fire questions and try to answer the remaining ones here. Okay, where were we? Also, because my voice is going by now, as you can all hear. So we're going to do quick fire answers here. There was a comment from Scott that drinking new and odd types of tea during the stream should be a recurring theme. Yeah, I have random teas in the house, and sometimes I drink random teas, and sometimes I like them, sometimes I don't. Often I do. Okay, we covered these questions, then we got into the cloud chamber. I think we aren't actually too far away from answering all the questions. There was a digression or comment from Pathfinder here about spin and how we use spin with quaternions. It is a very cool topic. I'm not going to go into more details about spin and quaternions here. It is a very cool topic, though. Okay, going back to the questions. I think I might have answered most of them by now. There was a random comment here about investments. I think that was a spam comment. Okay, yes, we are pretty much up to date. Comment from Fortining, cayenne pepper and hot tea sometimes helps with cough. Yeah, cayenne pepper does. I love cayenne pepper. I am currently on a bit of a bland diet because I had a stomach bug that lasted almost 2 weeks. I have not had spicy food. I love spicy food. I love chili. I love cayenne pepper. I have not had spicy food in like 2 weeks, and I'm still on no cayenne. But yeah, I think cinnamon would also help. Ginger would also help. There's a lot of things I can put in my tea that would help with a cough. But as we have established, this is an old tea today because I didn't have my good teas at hand. Okay. Comment from Shawnee here. Do we know if time is a wave or particle? And if we could tilt our light cones, could we observe the past? Excellent questions. This goes back to something we were discussing last week of what is time. Time is not really a particle or a wave. Time is a dimension. In the same way that we have three space dimensions, up, down, left, right, in, out, we have a dimension of time. We need time to tell us when events happen. We can also see time as being the progression of entropy. So entropy is the maximum chaos in the universe, or the amount of chaos. The universe always tends to higher entropies. In general, a closed system that you don't act upon will tend to maximum entropy, to maximum chaos, and yes, the amount of chaos is going to increase, the amount of entropy is going to take over. So we can use time as kind of the passage of entropy. Time gives us how event A goes to event B. If I have a coffee mug and I drop it on the floor, we know that it started in one piece and then broke. We don't expect it to spontaneously assemble. So there is a clearly defined direction here. So time is the dimension. Time can be thought of as entropy, but time is not a particle or a wave. It is really just the way we explain how events happen in the universe. Now, as for if we could tilt our light cone, so a light cone is kind of our depiction of the universe, of space and time. So we often draw something like this, where this is point zero and time goes upwards. So this is kind of our light cone. Let me actually make that a cone so that we know what we're talking about. This here would be a light cone. And the idea is we're here. This is our future light cone. This is our past light cone. Everything here in the past leads us to this point here. Everything in the future are these possibilities here. So you can imagine these are the space coordinates, and we're going upwards in time here. So if you move along here, you would be traveling at the speed of light. So this is kind of representing space-time. It's a mathematical way we can represent it. Time goes upwards here. So we live in this part here. Everything that came before us is stuff we have access to, and we can only access stuff in our past light cone and in our future light cone. We can't access things outside of our light cone because that information would have to travel faster than light to reach us. So the question of if we could tilt our light cones, could we observe the past? I'm not sure how you want to tilt your light cone, because this is just a representation, right? It's not something you can actually knock over. If you wanted to tilt it, what you would be implying here is faster than light travel in one direction. Like if you wanted to travel faster than light, you'd be out here. And then could you steer back? You'd still only be able to see the things inside the light cone. So if you were able to tilt this, for example, by traveling faster than light, we're not sure because that technically isn't feasible. But yes, you can see into your own previous light cone. This is when we look into the night. You can't just rewind your light cone and play it back, but you can see information from your previous light cone, and anything in the future lies in your future light cone. So I'm not sure about tilting the light cone, but it is a way that we visualize space-time. I know last week we had a long conversation about how to visualize space-time. Often how physicists visualize space-time is with a light cone. Light cone makes things both easier and more complicated. Okay, going back to questions. I keep feeling like I caught up with questions and then see there's still a lot of scrolling left to be done. Okay. There were more questions here. Light cones are cool and all, but I prefer ice cream cones. Yeah, me too. Okay, let's keep on with the questions here. There's only a few left to answer. I'm going to try to answer all the questions and then we're going to wrap it up. My voice has settled down, which is good. Coughing fit over. Another question from Shawnee. Great questions from Shawnee today here. And usually, I think you've been in the stream before, but great questions today. Do you consider cosmologists to be more self-aware of their places in the universe than everyday people? And do you think that people could benefit from this universal knowledge? Um, so I don't think that being a cosmologist gives me any special insight or like deep philosophical reflection about my place in the world. I feel like just being aware of the size of the universe makes it a bit easier to realize that we are tiny and insignificant, and nothing we really do has a big impact on the overall universe. But that is also reassuring because we exist for a small fraction of a time in the history of the cosmos, and we can't really impact the universe. You know, even if we burn our planet, the universe won't care. But we are here. We are bearing witness to the universe, and we are part of the universe. We carry atoms that were produced 13 billion years ago in the Big Bang itself. We carry this within us. We carry stardust in us. We carry universe dust in us. So we are connected to the universe. I don't necessarily feel like I have a deeper understanding than everyday people about our place in the universe. I'm not sure. I feel like this is something that is not necessarily tied to being a cosmologist. You know, in general, I know some cosmologists who are very much lacking in self-awareness, and I know some cosmologists who are very deep and reflective about things. I think in general, this is everyone is nuanced, right? And this goes into the idea that scientists are just normal people and everyone has nuances and different ways of viewing things. I do think that studying the universe is a good way to remind ourselves of our place in the universe. But I'm not sure if it necessarily brings any clarity or any deep insight. I do think everyone could benefit from reminding themselves from time to time of how big and scary and ridiculous and amazing the universe is, because it's really cool. I'm not sure if it would solve many problems. You know, a lot of science a lot of astronauts when they go to space they come back and they say that they've gained a new clarity of like seeing the earth as a spaceship that we all co-inhabit together and that we need to help each other out. And you know, if going to space is what it takes for people to have this realization, great. I don't necessarily think that means we should send everybody to space. So I feel like that's a very cool question, and I'm not sure if I have a good answer to it. I think it's good to be aware of how tiny and insignificant we are on cosmic scales, but also how deeply connected we are to the universe. I think it's good to be aware of these things. I'm not sure if that will bring clarity to people. I know some people find it very scary to consider the size of the universe, or a bit overwhelming. And you know, I don't necessarily think that studying it brings this clarity, but I think it's a good thing to know. And it's good to be aware of kind of our place in things. But yes, it's it's a very cool question, and I feel like we're going to get very philosophical with that question. But it's a cool question. Comment from Prathia, you know you went too deep when the cosmologist warned you that we're wading into the hypothetical. Yeah, when we start talking about multiverses, that's when I need to bring out the disclaimer of we don't know what we're talking about here. This is no longer theories, this is hypothesis. We have left the realm of what we know. We have gone into the realm of the unknown, which is not the quantum realm, despite what you might think. Despite what sci-fi tells you. I'm gonna make so many sci-fi fans. I'm like, you know, I do actually love sci-fi. And I do love some films, but I know I keep bashing a particular franchise of superhero films. It just happens. I you know enjoy your films. I'm gonna stop complaining about the quantum realm probably for about 30 seconds. Okay, comment from John here. Do you think the inflation multiverse is related to the quantum many worlds multiverse? Not directly. So the quantum multiverse idea is the idea that every action opens up a parallel world where anytime there's like this random chance of the entangled electrons being up and down, when you make that measurement, you branch the universe, and one universe has one outcome, the other has another outcome, and every possible decision leads to a branching universe where maybe in the grand scheme of things nothing changes, maybe things do. So this is not necessarily the same as when we talk about the inflationary multiverse, where we could have multiple versions of the universe with different laws of physics. But I do think the many worlds interpretation of quantum physics is very interesting, and it's a cool one to think about. But I wouldn't necessarily say they are connected. Honey water helps with dry cough and to rest someone's throat. Yeah, yeah. The problem is this is just persistent. I appreciate everyone giving me remedies here, but this is a persistent cough due to my chronic illness, and I can take things to soothe it, but it's a short-lived effect. Comment from Prathia, because when I mentioned spicy food, did you enjoy food in India? Yes, yes, yes. So I love Indian food. It is my favorite food. And I was lucky enough to go to India for a wedding in December last year. It's already been a while. It was an amazing experience, and I loved the food so much. And I probably ate my body weight in paneer in the few days that I was there, because paneer is the best thing ever. Yes, I very much did enjoy the food in India. We also had a lot of chat, a lot of like street food. And yes, I loved the food there. That was very much something I'm craving these days when I've not been able to eat anything overly flavorful in a few weeks. I'm definitely craving paneer and some chat or something tasty. Yes, yes, I did enjoy the food in India. Okay, going through the questions quickly. If we could put time through a double slit, we may be surprised. Yeah, put time through a double slit experiment and see what happens. That would be interesting. Also, speaking of food, I have to ask: it's kebako a big thing there? Kebako, what is kebako? I I feel like I've heard that word, but I'm currently not sure exactly what kebako is. Is it just a kebab? No. What is kebako? I'm not sure what kebako is. I know that's what is good. Is it? Yeah, it's just kebab. It's just yes, like meatballs. Yeah, I think you're asking the wrong person there. If kebab was a big thing here, because I am vegetarian, mostly vegan actually, with like exceptions for paneer. So kebab is a meat-based dish in Finland apparently. It's not something I'm familiar with because I don't eat meat. Okay, let's see more comments. Did you or someone you know have existential crisis during college or work because of the studying the universe? Absolutely. I mean, in general, I have existential crises on a regular basis because I have a lot of anxiety. I have a lot of existential crises in general. So a lot of people I know how, especially in academia, have existential crises about random things. As to existential crises, once you start figuring out are like the size of the universe, yes. There were definitely some very interesting conversations that we had in our undergrad after certain cosmology lessons. Some of us would then go out and chill afterwards and get into really deep conversations. And I do feel like studying the universe is a really fun way to scare yourself, but it is very, very cool. It is a fun thing to do. And yeah, there's definitely some fun conversations you can have there. I think actually the conversations I enjoyed the most. So there were two people in my undergrad who were deeply religious, and they were studying physics, and their response to that was, I want to know more about the universe that God has made. And it was really interesting to discuss with them how they were bringing together their religious beliefs and their scientific beliefs. That was super interesting, and I think those conversations did trigger a lot of deep thinking in a lot of us in those chats. And it was really interesting. But yes, I do feel like studying cosmology is a good way to trigger an existential crisis. But I feel like that's also true for a lot of things. As humans are very, very anxiety driven. So there's a lot of things that can trigger different crises, different existential crises. But yes, I think there's a video called like Power of 10, which gradually zooms out on things, starts from an atom and zooms out to see the whole universe, and then zooms back in. And watching that video is always a bit like, whoa, everything is tiny. So yes, there's yeah. Just finished the best sci-fi book, Long Way to a Small Angry Planet, really fun and different. That is Becky Chambers, is it not? That has been on my to be read list for a very long time. I've heard a lot of really good things about those books, and I do want to read them at some point. I don't read as much sci-fi as I used to, but Becky Chambers has been on my to be read list for a very long time. Yes, I've heard good things about that. Okay, I think I've answered all the questions. Took an hour and a half today, but we got there. I think I've answered all the questions. If not, let me know. If I overlooked a question, put it here again, and I'll try to answer it. I feel like we did address all the questions, and in any case, 90 minutes. We are definitely going past the 1 hour mark. That is the standard for Cup of Cosmology. So you can't complain. A lot of you used to ask for longer streams that was more than 1 hour. 90 minutes today. This might be the record in quite a while. So longer streams, you can't complain. Okay, thank you everyone for joining. This has been great fun. I've loved all of the super cool questions. We've had some broad topics today. We talked about cloud chambers for a while. We talked about primordial black holes. We've talked about time, light cones, about inflation, about dark energy. There have been a lot of very broad, very cool topics. So as always, thank you everyone for all the questions. When I come to do an Ask Me Anything, I really am relying on you all coming up with questions because I don't have a topic ready. So if you don't ask questions, I need to just kind of improvise on the spot, which I do anyway with the questions. But at least when you ask a lot of questions, it gives direction to the stream. And I really appreciate it because I come here like, let's see what they'll ask today. Then we get fun questions. There was the final comment from Prathia. Why not both? The multiverse is large enough to fit both many worlds and the different laws of physics, universes, and their Cartesian products. Yeah. Why not both? I feel like that is my default answer to things when given an A/B option. My answer is both. But yeah, we've had some super cool questions today. It's been really, really fun. So next week, I think I'm going to do a topic that I've been promising for a while. Next week, if all goes to plan, I'm going to do a stream called The Ups and Downs of Academia. The things you know, the things you don't know, the good things about being an academic, the bad things about being an academic, the things people don't want you to talk about, and the things we have to talk about. It's going to be a heavy stream. It's going to be heavy hitting. It won't be more than 1 hour. And yeah, that should be next Sunday. I might have to change it depending on life things. But in principle, next Sunday, I'm going to do the stream of The Ups and Downs of Academia. And yes, this is absolutely something I've wanted to do for a while. I've been thinking about it for months, and I feel like I'm in the right headspace to do this now. So maybe next week, next Sunday, we get The Ups and Downs of Academia, the good, the bad, the ugly, the evil, all of the fun. The next stream will be Sunday next week, same time as always. That is 8 p.m. if you're in Finland, like me, 7 p.m. if you're in mainland Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. There is a time zone converter on cupofcosmology.com where you can figure out when the next stream is going to be in your own time zone. Of course, if you want to be notified for the next stream, make sure you subscribe to the channel, turn on notifications, and you will get a notification 30 minutes before I go live to make sure you don't miss it. So make sure you subscribe, leave a comment, like the video if you haven't done so already. It really, really does help. And I appreciate all of you who do the YouTube and Twitch things to gain these videos more traction. Been super fun today. I've loved all of the questions. Been some really, really cool questions, really cool topics. Now it's time to rest. So thank you everyone for joining. This has been super fun. I hope to see you all again next Sunday, same time as always. And I hope in the meantime, you all take care of each other and stay curious.